Hello, today I am presenting our EEE304 laboratory project along with my other two team members. My name is Raisa Binta Hussain, student ID 1606151. Our project is traffic light controller using finite state machine. Before explaining the implementation of the project, let us see how the design will work. The controller is designed for a 8-lanes 4-way junction. It will let the cars from north to pass first. Cars from north will be able to go all the other 3 ways. For this purpose, the traffic light on north side have to be green and the other 3 sides have to be red. This state will remain for 8 clock cycles. After the north side, cars from south, east and west will follow the same process and then it will return to north again. Now come to the yellow light. Yellow light will be on for 4 clock cycles when the light switch from green to red and vice versa. To understand it better, let us see the color switching sequence of the system. It will be green, yellow, red, yellow, and then green again. This process will go on. The duration in clock cycles are written here. Now, let us see the inputs and outputs of the system. We have 4 outputs here: N lights, S lights, E lights, and W lights, denoting the traffic lights on north, south, east, and west. Green, red, and yellow lights are noted as this in our code. We have only 2 inputs, clock cycle and reset. The design will start working on the negative edge of the reset and change on the positive edge of the clock cycle. For each side, we have defined 2 states. One is for green light and another is for yellow light. For example, in north state, the green light state is north. In this state, the N lights will be green and the other 3 lights will be red. And for north yellow state, the N lights and S lights will be yellow and other 2 will be red. This process will be same for the other 3 sides as well. So in total, we will have 8 states. Now if we look at the code, the output and input are denoted here and the parameters for each state are mentioned here. For the first part of the code, we have defined all the states here. If we look at this, there are north state, north yellow state, south state, south yellow state, and so on. Now, if we look at the code, the outputs and inputs are declared here. Each output is a wire of 3, and both the inputs are wire of 1. For the first part of the code, it will work to switch the states. This part will be explained by one of my partners. Let us concentrate on how each state will give output. As I have mentioned earlier, the green is denoted as binary 001, yellow as binary 010, and red as binary 100. We have used simple case statement to assign the value of each output. As an example, if we look at the south state, in south state, the south lights will be green or binary 001 and other 3 lights will be red or binary 100. For south yellow state, the south light and the east light, which will come next, will be binary 010 or yellow and other 2 lights will be binary 100 or red.
Welcome to student ID 6006147. Our project is traffic light controller. Here is our Verilog code. In this Verilog code, we can see that we have 2 input, clock and reset signal, and count and state is the internal variable which changes according to the counter system we have built for this project. We have 8 parameters to define the states: state north y, south y, east y, west y. For north, we have north Euro state. For south we have south Euro state, and for east we have east Euro state, and for west we have west Euro state. And we have 4 output signals: north light, south light, east light, and west light. So in our sensitivity list we have clock signal and reset signal, which we have for input. For positive age changing in positive age, if the clock changes in the positive age, and reset A also in the positive change, the output changes. And if the reset signal is 1, the counter starts 0. When the reset signal is 0, the counter starts. When the reset signal is 1, the counter starts from a north state north, and whenever the reset signal is 0, the counter begins to start from 0 0 0, and the state changes when the count for state north goes from 0 to 7, and this count plus 001 indicates that the counter counts start from 000 and goes to 007 to give the 8-second delay for the north state. And after north state we will go to the north y state. In north y state we will have a delay of 4 seconds. In these 4 seconds the counter again starts from 0 and increment by 1 to go for 4-second count in north y. Again in the south system, in the south state, again the count goes from 0 to 7 to give the 8-second delay, and in the south y state again this will give us the 4-second delay. In this way we have designed the 8 states, and after every 8 seconds the counter counts goes from 0 to 7 and the state changes. We can see this also by our state diagram. In our state diagram we have given a reset signal and the north state. The north state is the state 0. Whenever there is the count goes from 0 to 7, the state changes and it goes from north to northwest state. And if the count goes from 0 to 3 to give the 3-second count, then the north y 0, it will be in the north state until the counter goes from 0 to 7. When the 7 is crossed, the north changes to north y, and in the north y state we can see that it will be in the north state until the count goes from 0 to 3 to give the 4-second delay required for Euro state. And again the north y state changes to south state if the counter count changes from 0 to 4, 0 to 3. Whenever there is the change occurs, whenever the counter goes from 0 to 3 and when the 4 will come, the state will change from north y to south. Again the south state changes from south y when the 8-second delay is completed by 0 to 7, and until the 0 to 7 countdown is completed, the state will be in the south state. So in this way the 8 states will be counted in our counter, and in the last state west y we again go to the north y state, the north state, and this way the complete state machine. We will be showing our project output by Intel FPGA Starter Edition Model SIM, where we have this traffic signal Verilog coded input in model SIM, and we have this input and output clock and reset as our output, as our input, and north, south, east, and west lights as our output, and the internal variable state and count changes shown by these two variables. We have the state and count in radix unsigned to see the decimal changes to 0 to 7 and 0 to 3 to know the changes in the states, and count 0 to 7 and 0 to 4. So the signal wave has been added in the output menu in the wave output, and whenever we are modified a clock signal in the clock wave, will give a 50-second period to have a 50% duty cycle, and a reset signal will have a clock of 5000 and a reset of 5 to have minimum changes. Now if we compile it, run 100, here we can see that the run is completed by model sim, and the output will be shown here. Here we can see that in the clock positive age, the output changes from 0 to 1, and the state changes from 0 then to 1, then 2, then 3, then 3, 4, 5, 6, and 7. And after the 7th state, there will be again the 0 state, which accounted for the north state. So whenever we are in 0 state, the count starts from 0 and goes to 7. And whenever the north state count goes from 0 to 7, the output for the north state will be 001, which will have the green light. In the north state, we will have the green light, and all the other 4 directions light will be red, 100. When the state changes after 8 seconds into north Y, the counter state changes to 1. And for 0 to 3, this means for 4 seconds, the in lights will be on yellow and the south lights will be yellow. But the other 2 lights will be 100, which means red. The state changes again after 3-second yellow state delay and 4-second yellow state delay, and in the state 2, the output, the state count output is changed again to 0 to 7, give the 8-second delay, and in this time the output in lights will be 100, which means this is the red light, and the south light will be the green light, but other 2 lights will be red. So in this way, we can see that the states changes according to the count values. Whenever we are in north, south, east, and west states, the counter counts 0 to 7. And whenever we are in north Y, south Y, east Y, and west Y states, the counter counts from 0 to 3 to give the 4-second delay into the Y states. So this, the Verilog code output matches with the model sim.
Hello, this is Proshun Dotto. I am here to present the Proteus simulation and the PCB design part of our project. As it can be seen, we have designed a timer or clock, then a 4-bit counter, then some combinational logic circuit, and then animated traffic light. As it can be seen from our circuit diagram, we have designed 4-bit up counter with the T flip-flop. But in the circuit diagram, we have used JK flip-flop by shorting both the inputs of the flip-flops. The 4 LED lights presented here are used to observe the outputs of the flip-flop. They will behave according to this truth table. First, TD will be green, then TC and TD will be green simultaneously, then TD will be green, then TC, TD, and TB will be green simultaneously. Let's move on to the circuit. This is the TD flip-flop, this is TC, this is TB, and this is TA flip-flop. So first TD is green. After that, TC and TD will be green simultaneously. Then TD will be green. After that, TC, TD, and TB will be green simultaneously. Here, the equations of the outputs of the flip-flops have been calculated using the K-map minimization technique. These are presented in our reports. Since there are 4 flip-flops, there will be total 16 counter states. These are presented here. At the initial counter state, north and west light will be on yellow. Then north will be green for the next 3 counter states. During these counter states, the rest of the 3 lights will be on red. After that, north will again be on yellow, and simultaneously south will be on yellow also. After that, north will be on red for the rest of the counter states. Now let's move on to the circuit diagram. For observing the output, let's minimize the clock's frequency. So here first north light is yellow and west light is yellow also. Then north will be green and west will, and the rest of the three will be red. After that, north and south will be in yellow states. Then south will be green and north will be on red. This pattern will follow until the west light becomes green, and with that this will follow or complete the counter state table presented here. There are some interesting facts. From green to red transition, there will be an yellow state. It means that whenever the lane which was on green will not be instantaneously on red state, there will be given some time to halt the vehicles, which is imitating the real world application. Now let's move on to the PCB circuit diagram. It was a two-layer PCB. The red wires are on the top copper layer and the blue wires are on the bottom copper layer. In this PCB design, some PCB packages were not available, like the LED green PCB packages, clock and logic state PCB packages were not available. So these PCB packages have been designed manually. Now let's look at the 3D visualization of our circuit. This is the 3D visualization of our circuit. This is the front part. This is the back view. Now let's move on to the top silk diagram. The top silk diagram of our PCB is highlighting the devices and ICs used here. This is the top circuit diagram, which is the connection diagram basically, and this is the bottom copper connection diagram. So that's all from us. This was our project traffic light controller using FSM with the implementation in Proteus.